Welcome to session 20, Recent Advances in Brain Network Statistics. My name is Qiong Wu. I'm a PhD candidate from the University of Maryland, College Park, and it's my great honor to chair this session. In this session, we will have 3 talks followed by a floor discussion for Q&A, and you are always welcome to use the chat box to type in your questions. Our first talk will be given by Dr. Jesus Arroyo. He is a postdoctoral fellow in the Department of Mathematics at the University of Maryland, College Park, and an assistant research scientist in the Department of Applied Mathematics and Statistics at Johns Hopkins University. His research work includes statistical network analysis, machine learning, high-dimensional data analysis, and application to neural imaging. His title for today's talk is Inference from Multiple Heterogeneous Networks with a Common Invariant Subspace. Jason, you could get started once you are ready.
Thank you very much for the invitation to present, and thank you to the organizers for the conference. So today I'm going to be talking about statistical inference for multiple network data. This is some work that I have done during my postdoc with multiple people at Johns Hopkins, with Avanti Arroyo, with Joshua Cape, who's now at Pittsburgh, Qiong Chen, Carrie Priv, and Joshua Vogelstein, who are my postdoc advisors. So before starting into the topic of today, let me give some motivation of the idea of how do we want to model multiple networks. So the main motivation of our approach is on latent space models for networks. The idea of these models is that the vertices are represented as latent vectors in some d-dimensional space. We can encode them in a matrix X, and is going to denote the number of nodes in the network. So for each vertex, we assign a vector, and we just stack them into a matrix X. Then this type of models allow for a very general type of distributions for the networks. And the idea is that the edges of the graphs are going to be conditionally independent given the knowledge of these latent positions. So the distribution for each particular edge between vertices U and B is just going to be a function of the latent positions for vertex U and vertex B. This function G is typically some similarity function that indicates how likely is that 2 vertices are going to connect in the network, and F is some distribution according to the type of data that we are using. So for example, here I have a brain network from fMRI, and after computing the embedding of this network into 2 dimensions, we can see that each of these points represents a vertex, and these are colored according to the brain systems. So with this type of models, we can capture certain similarities between vertices. So for example, here, if 2 vertices are close in this space, they are going to be more likely to be connected. And we can see that the colors kind of cluster according to the brain system. So this type of models can capture important structure in brain networks and in other networks as well. So one particular type of latent space models is the random dot product graph, or RDPG for short. And so this model is in particular for undirected and weighted graphs, but it can be extended for more general distributions. But for today, I'm going to be focusing mostly on this type of networks. So A is going to be a binary adjacency matrix, and it's going to be symmetric because the networks are undirected. And under this model, the particular type of function that characterizes the edges is the dot product. So for each pair of latent positions, we're going to encode the probability of connection in a matrix P of size n by n. And the entries of this matrix are going to be given by the dot product between 2 latent positions of the corresponding vertices. So then we can generate the edges of the network as just Bernoulli random variables according to these probabilities. So here's one example of this random dot product graph. So initially we have latent vectors. Here it's in a 3-dimensional space. So each point represents a vertex. Then we can encode them into a matrix P. And this is basically just going to be given by the dot product between these vertices. So we can write it in the matrix notation in this way. And then the network A is generated by independently taking a Bernoulli trial on each of these entries of the adjacency matrix. So this is how the final network is going to look like. So the random dot product graph framework is very useful for multiple reasons. So on the first hand, it's a very flexible model, and it allows to characterize many other classes of particular models of interest for network data. So for example, the stochastic block models that capture community structure in graphs, or more generally low rank models. And it also provides some approximation to other non-parametric type of models like graphons, for example. And another reason for the interest in RDPG models is the computational tractability, because it's very easy to estimate the latent positions by just doing an eigendecomposition of the adjacency matrix, and then taking defining this x tilde as the leading eigenvectors times the square root of the eigenvalues. This is a method called the adjacency spectral embedding, and it has been theoretically justified for RDPG models. In particular, this x tilde is consistent and is asymptotically normal for the true latent positions of a random dot product graph. And finally, this method is also practically useful. There are multiple applications of interest to subsequent inference problems. So for example, for community detection, we can take the estimated latent positions and cluster them in order to identify communities in the graph. We can do vertex classification if we know the labels for some of the vertices and then predict the labels of the rest. It's also been used for graph hypothesis testing in order to compare two networks, or for manifold learning problems where these latent positions lie in a lower dimensional space. So all of these have done for a single network, but the goal of today's talk is to extend these results for multiple networks that can capture different cases of interest in the data. So in particular, we're going to focus on networks with aligned vertices, meaning that the same vertex is going to represent the same entity across all the networks in the data. So for example, this is a common setting in the samples of networks, like in brain imaging, where each node is representing the same brain location across different subjects, and the networks are a measure of the connectivity between two brain regions. And another application of this type of ideas is on time varying graphs, where the network is changing over time and some edges are appearing or disappearing. And finally, this is also the setting for multi-layer networks, in which we have different modalities of the data representing different types of relationships. So for example, in imaging data, we may have DTI or fMRI networks from the brain. So, well, as I mentioned earlier, there's a lot of work for single network, but our purpose in today's talk is to present a model that is able to extend some of these ideas to the multiple network setting. And in multiple networks, there are two main questions that we want to solve typically. So on the one hand, we're interested in learning something about the vertex properties that are common across all the sample of networks. So for example, we may want to do community detection, but instead of just taking a single graph, we want to gather the information that is represented across all the networks, and vertex classification, or find associations between vertices and attributes. And these are for common vertex properties. But on the other hand, we are also interested in learning something about individual networks. So we may want to do hypothesis testing both for comparing two networks or at the population level in order to compare populations of graphs. And we may also be interested in clustering graphs or doing classification or prediction of certain attributes. And in order to deal with multiple networks, there are some challenges that appear in this setting. So on the one hand, we want a model that is able to characterize the heterogeneity across graphs, meaning that each of these networks is probably going to be a little bit different from the other, and it's going to have different structures, but at the same time, there's something common across all the graphs. So that's particularly in the setting of brain networks, where they are always referring to the same anatomy, but each particular person may have its own characteristics that differ from the rest. So we want a model that is able to characterize this heterogeneity very well. Another issue is the high dimensionality, because typically we have a small number of networks, but the number of parameters in the data is large. And that creates problems in terms of computations, because we want to have models that are easy to fit and have theoretical guarantees for these algorithms. So the model that I'm going to present today is this model that we call the Common Subspace Independent Edge Model, or COSI for short. And the idea of this model is that we have two sets of parameters. So we have a matrix V, which is a matrix of size n by d, where d is the embedding dimension, n is the number of vertices in the networks. And we're going to assume that this matrix has orthonormal columns. And we also have a collection of score matrices, R1 to Rm. So each of these matrices is going to represent the specific connectivity for one graph. We are assuming that we have m graphs in total. And this model, the COSI model with bounded rank D, is going to be defined according to this equation. So essentially, the probability of each edge in the network is going to be given by this product of B, Ri, and B transpose. So the intuition behind this model is the following. So on the first hand, each network I is going to have its own probability matrix, and all of them are going to have rank at most D. And this matrix V is going to be the basis of the common invariant subspace for all the networks. So I'm going to give some motivation of this common invariant subspace in the next slide. But for now, you just need to assume that these matrices have exactly the same invariant subspace, but we are not assuming that they have the same eigenvectors. They only share the invariant subspace. The eigenvectors can be different. And the interpretation of this model is similar to the RDPG because we can represent the rows of this model as latent positions. And then these probabilities for each edge are going to be given by the inner product of these latent positions with some matrix Ri in the middle that is going to change for each subject. So essentially this matrix is allowing to have different connectivity for each particular network, but there's a common structure across all the vertices. And we're going to call Ri the score matrix because this is representing the scores after projecting the network into the common invariant subspace. So to give some motivation of this model, we can represent with these multi-layer stochastic block models in which we have some common community structure across all the graphs, but each graph may have different connectivity patterns. So for example, we may have graphs that are more connected within communities or assortativity structure, or also core periphery structure. But the idea is that the communities are the same, but the connectivity is varying across all the graphs in the collection. So this allows to capture heterogeneity in the data. But more generally, we can extend the ideas of RDPG graphs into this multi-layer setting, and many specific cases for a single network can be translated into multiple networks by using this framework. So that's essentially the motivation for having a common invariant subspace in the model. So now, in order to estimate the model, we developed this algorithm that we call the multiple adjacency spectral embedding. And the idea of this method is that, first we're going to perform individual embedding for each network, the adjacency spectral embedding. And that is going to give us some information about the common invariant subspace. But in order to gather all this information and to estimate just a single set of latent positions for all the networks, we compute an SVD of the concatenated ASCs. And this SVD is going to be the estimator of B in the model. And then after estimating B hat, we are going to project each network into this common invariant subspace. And that's how we get the score matrices, by just multiplying B transpose A, B. So now let me just give you quickly some properties of this model. Based on this method, we can estimate the common invariant subspace consistently. This is the result that we have for the error in estimating V. And essentially what this theorem is telling us is that the expected error in Frobenius norm between B hat and B is going to be bounded by this quantity that goes to 0 as the number of vertices goes to infinity. But the term that dominates in this rate is the first one, which contains an M here. M is the number of networks in the data. So essentially, this rate is going fast to 0 when we have more, a larger sample size of networks. So the intuition of this theorem is basically that we are able to gather information across graphs and reduce the error by averaging multiple networks in this way to get an estimate for the common invariant subspace. And this rate can be translated into something that depends both on n and m, which is the term that dominates in the case of having dense graphs in particular. And it has some applications for community detection that I'm not going to mention today due to interest of time. The second result that we have for the parameters of the model is asymptotic normality of the score matrices. So this theorem is telling us that we can characterize the asymptotic distribution of the score matrices. So R hat is the estimated score matrices, R is the true score matrix. We have to introduce some orthogonal matrix here because some non-identifiability issues in the model that can be solved in certain cases that I'm going to mention later. And we also have some matrix H. This is some bias term that goes to 0 as the sample size increases. And this equation converges to a normal distribution with some covariance sigma. And we can calculate this sigma using the parameters of the model B and PI. So essentially what this result is telling us is that after a proper alignment of this R hat and Ri, we can show that it converges to a normal distribution. And this is going to be useful later for developing a hypothesis test for comparing networks. So now let me give you an application of this methodology to the HNU1 study. So this study contains data from multiple healthy subjects that were scanned repeated times over a period of 1 month. This is diffusion MRI data. And for each network and for each person and each scan, we're going to obtain a network that is going to represent the structural connectivity of the brain by measuring the existence of nerve tracks between different brain regions. We have a total of 200 brain regions in this study. And because there are 30 subjects and 10 scans per subject, in total there are 300 graphs that can be stuck in this matrix way, for example. So the idea of our model is that first we're going to perform this embedding by fitting the causing model using the maze algorithm that I mentioned earlier. So something that I didn't mention when I presented the algorithm is that for the theory and purposes of the method, we assume that this is known, but in practice, we need to estimate this, which is a problem with estimating the rank of the matrices. So we do that by script plot. For example, there are other methods to do it, but here in particular, we chose the script plot to fit the model, and we estimated that the embedding dimension is equals to 15. So this model is going to produce 2 embeddings. The first one is a vertex embedding that I have here on the left. So each point on this embedding is representing a vertex of the networks. And as we can see, the points are colored by according to the hemisphere of the brain. So essentially, the first 3 dimensions of this embedding are capturing very well the anatomy of the brain by splitting the data into left and right hemisphere. The second embedding that we can obtain with this model is for the networks. So here, each point in the embedding is representing a different network in the data. So the networks are colored according to subject ID because we have 10 networks per subject. And what we can see in this embedding is that networks of the same subject are close in the space. So essentially, this is telling us something that the connectivity of a person is characterizing very well the specific individual. And actually, so according to our theory, if these points were coming from the same probability matrix, we would expect that this cloud point would be normally distributed around a certain specific mean for all the graphs. So that's the idea that we're going to use to perform hypothesis testing. So here I have the results of hypothesis testing between all the networks in the data. So we have these 300 networks. So in total, we have 300 choose 2 different hypothesis tests. And we are just testing whether or not the 2 probabilities that generated the networks are the same. We use as a test statistic the estimated score matrices from the model. So basically the distance between these score matrices can tell us how similar they are. In order to compute the null distribution, we have 2 different ways. One is derived from the theory based on the asymptotic null distribution. The second one is using a parametric bootstrap approach. So I didn't show you the simulations for the interest of time, but generally what we observe in the simulations is that both these methods are similar in the case that the assumptions of the theory hold, which is expected. But when they do not hold, the p-values for the asymptotic null distribution might be a little bit inflated. So that's one disadvantage in practice. But the advantage is that the asymptotic null distribution is much faster to compute than the parametric bootstrap. But what we can see in these plots is that the model is characterizing the variability in the data very well, because pairs of networks that correspond to the same subject are represented in the diagonal blocks of this matrix, and they typically have large p-values, meaning that the model is not able to reject the difference between networks corresponding to the same subject, and at the same time, the model is also distinguishing networks of two different subjects because the p-values are very small. So we also analyze this from a different perspective. Here we perform graph classification. So the idea is that we want to predict the label of a specific network, well, according to the subject label, by first embedding the network into d dimensions, and then doing a cross-validation to predict the label. We compare multiple methods for doing this problem, and we plot them as a function of the number of embedding dimensions and as a function of the parameters used in the model. And what we observe here is that in general, there are multiple methods that can classify the networks very well. But this model, the COSI model, is in particular getting the best accuracy for a smaller description length, meaning that we have to pay a smaller price in the number of parameters to get the accurate classifier of the networks. So this is all for today. And just to summarize, the method that I presented is flexible and tractable, both computationally and theoretically. And it has some applications to subsequent inference problems like community detection, classification, hypothesis testing, or dimensionality reduction. And we have some ongoing work and future work on these ideas. First, to extend this framework to population level inference for multiple networks, and also to understand when we have correlation between the networks, how does the inference get affected by that? So that's all. Thank you very much for your attention. And here's the reference of the talk.
Now we will have our second speaker, Dr. Qiong Chen. He serves as a mathematical statistician in NIMH. His work mainly focuses on statistical modeling, Bayesian inference in neuroimaging data, and developing statistical tools in AFNI. His talk today is improving reproducibility in network modeling. Okay, we could get started.
All right. Excuse me. Hello, everyone. This is my first time attending this conference. Oh, sorry. Some reasons. This is my first time attending this conference. Thanks for all the conference organizers, and also thanks for our session chairman and the organizer. So my talk is about hierarchical modeling. So first, I'm going to briefly review the current and dominant approach and massive univariate analysis. So what are the pluses and the minuses? So I'm going to address some of the limitations by proposing Bayesian multi-level modeling. So I'm going to start using two specific data sets as demo situations to show how the Bayesian multi-level modeling formulation could improve efficiency and address overcome some of the limitations of the traditional approach. So first, let's talk about the main approach, right? Mass univariate analysis. So in that case, regardless what data you have, it can be whole brain voxel-wise data, or you have a bunch of brain regions, or you have matrix data, or you have a DTI, you have bundles tracks, right? So in that case, we have different types of, I call it spatial units. So the traditional approach, usually we adopt, I call it a divide and conquer strategy. So we just say individual trees without the view of the whole forest. So that's what this strategy is about. So from modeling perspective, you can, at each spatial unit, you can do a t-test or general linear model and nova linear mixed effects model, et cetera, et cetera. So the nice thing about this approach is simple, right? So most people already learned this in basic statistics textbooks, right? It's intuitive. I mean, it's, most people can do it. There's no hierarchical structures involved. And computationally, it's very economical, right? So those are the nice things. But there's so many downsides. So one big thing, I think, the problem is informational waste. Why do I say that? First of all, the hierarchical structure is totally not taken into consideration, right? I mean, you have 100,000 voxels, or you have 10 or 100 RIs or matrix elements. You treat them as they're isolated. There's no common information is shared across those spatial units. So one direct consequence of that is you're going to pay the cost of multiple testing, right? So that's, I mean, in the field, after a while, there's a debate which method is more vigorous than others, right? So there's who is better than us, superior than others. So, but there are a couple of other issues too. I mean, overfitting, right? So if for those machine learning people, I mean, overfitting is at each spatial unit level, you're accurate, but you pay the cost for the overall predictive, pay the price of accuracy at the overall level. And for the multiple comparison issue, the big problem is in the end, you have to adopt a binarization step. You draw an artificial line in the sand marked by the magical number of 0.05, right? So you have to adopt that. Even though if your p-value is 0.051, then you're not allowed to show your results in public. And many other issues, like I'm going to talk about the conceptual issue. For example, Tom Nichols yesterday talked about the uncertainty at the cluster level. So whole brain analysis, people focus on the clusters. So the reason we adopt that approach is we don't trust the voxel level statistics, right? So in the end, we say this cluster survives the adjustment. So in that sense, since after that point, we should focus on the cluster level. We should not talk about the voxel values. But if you look at the papers in the field, the brain images, they show T statistic value at the voxel level. In the tables, they show the peak voxel T statistic values. Presumably, we'll talk about the cluster results. The voxel values are not even meaningful. The reason we do the correction is because we don't trust the voxel level T statistic value. So, but then people still display those results. That's one, I call it a conceptual inconsistency. Another problem is, once you have a cluster, I mean, the researcher would like to say, how is that cluster is associated with brain region? Now you need to go back, okay, let's forget about the cluster. Let's just focus on the so-called peak voxel, find the anatomical location. That's, for example, in amygdala or insula. Then you use that voxel's location to determine the cluster association. So you are back and forth, right? So that's, suppose your cluster is a little bit bigger, spill over to a neighboring brain regions. Are you allowed to talk about those neighboring regions? So this is switch back and forth between cluster and the voxels. Those are the issues at the conceptual level and the specificity problems. But the big problem is, to me, is when we adopt that divide and conquer approach, right? Mass unified analysis, implicitly, people make an assumption. That assumption, regardless it's voxel regions or matrix elements, the underlying assumption is those spatial units follow uniform distribution, right? So you don't have any prior knowledge about the distribution. That means it's a uniform from minus infinity to positive infinity. So that's the underlying assumption. But in reality, I mean, I think most people would agree with me, regardless of your data domain, most likely would be a symmetric, a bell-shaped distribution, right? I mean, it can be Gaussian or can be anything like a student T distribution, right? So that's a more reasonable approach. But if we ignore that prior information, we're going to pay a lot of cost, right? So the traditional statistical approach, they pay attention to the so-called unbiasedness. Yes, at each voxel, at each matrix element, you are unbiased, but you are going to pay the cost at the global level. Not the global level cost is so-called multiple testing or adjustment, right? Another problem I'm going to briefly mention is about I call it discrimination about the anatomically small regions. So because people have to pay the cost for multiple testing, they use some leverage. That leverage is used in the labeling voxels, the so-called spatial extent. So you pay that cost, then you are going to sacrifice for those small regions. Even though those regions may have exactly the same signal strength, what effective size, or even higher than those bigger regions, but since we're going to use the spatial extent as a leverage, then we'll have to sacrifice those small regions. So that's, I call it discrimination. Another big problem is I call it vulnerability or sensitivity to your data domain, right? So you have more data, more number of voxels, more regions, or more bundles, then you're going to pay higher cost. So the model is not to be able to adaptive to the amount of data. So that's why there's a magical tool called a small volume correction, right? So if your data clusters or your regions cannot survive the adjustment or correction, then you just reduce, you play around, explore the data, go fishing expedition, right? You have different ways to make your own adjustment, right? So those are the potential issues. So what can we do? Can we do something a little bit different? So I'm arguing that the Bayesian multi-level approach is one possibility. So instead of as many models as the number of spatial units, we just adopt one model for everything. Is that possible? Well, we'll see. So this is basically conceptually related to the traditional linear mixed effects model approach. But that approach would not work for at least two reasons. One is linear mixed effects model, you can make inferences for their fixed effects. But for those random effects, there's not much we can do about it other than estimating the variance. So that's one problem. Another problem, the distribution is pretty much limited to Gaussian, right? So in the context of neuroimaging data. So if we wanted to expand that to other distribution like student T or exponentially modify the Gaussian or log Gaussian, if you adopt those flexible distributions, then that's a big issue. So what can we do? What can we gain through the Bayesian multi-level model approach? Well, first of all, we can share information across those spatial units. there are different terms. People call it regularization, shrinkage, partial pooling, and there are many talks in this conference. People adopt the regularization like lasso or harmonization, across different size scanners, right? I want to point out one. I call it self-adaptivity. I want to address the issue in the field. If you change your data, like reduce your brain volume or limit the number of regions or matrix size, the traditional approach would, the cost for the multiple testing issue would be different. But if you adopt this hierarchical model approach, we have this self-adaptivity. So the sensitivity or vulnerability is way much less. That's what they call the self-adaptivity. So then, of course, then since we have one model, there's no multiple comparison issue, right? So because in the end, we only have one overall posterior distribution. Whatever inferences you want to make is you're going to randomly draw the data from that overall posterior distribution. So in that sense, we don't have multiple comparison issue. So we can do other things like cross-validation to check whether the model is good or not compared to the alternative models, right? So, and also we don't have to hide the results, even if the evidence is not strong enough. We can show everything. We don't have to hide. Then everybody can make their own judgment about the results. We don't have the complication about the twisted p-value interpretations anymore, but we do control some errors. Those two errors we care about is not a p-value, but we call it types M. M stands for magnitude. So incorrect magnitude and incorrect sign. We care those two types of errors instead of the traditional p-value. So that's our strategy. Let's look at the first data set to demonstrate the approach. So in this case, pretty simple. It's pretty much like you have some number of RIs for the task-related FM data. In this case, it's a later work data. It's a TDI. So we have some number of subjects in two groups. We focus on one property, the axial diffusivity, three of them. So there are two groups, right? So in the end, we want to look at the group difference in terms of axial diffusivity. So that's the traditional approach. Since we have 11 tracks, we just perform 11, in this case, two sample tethers, right? 11 of them. In the end, you correct for multiple comparisons. If you do that, maybe only a couple of the tracks will survive the penalty, heavy penalty. So what can we do differently? So we adopt one model. So in this case, we have three indices: I for group, J for tracks, K for number of subjects. So we assume it's a follow Gaussian distribution. Well, we don't have to. For example, we can adopt a student T distribution. If we assume the data is a little bit skewed or may have outliers, we can use student T or use other distributions. But suppose it's Gaussian. So the mean is we have three components, right? So three indices. So since we have two groups, so each group will have their own overall average. Then at each bundle or each track, we also have two group differences, right? So that's the second component, cosine sub ij. The last component, pi sub k, that's the subject level variability fluctuations. So we make assumptions on a Bayesian framework we call them priors. So we will have this one model, then we implement it, then using a stand. Then there's a program in Affinity available for everybody to use. So that's the approach. Let's see how this approach end up with for this particular data set. So remember, this is DDI. We look at the axial diffusivity. So 11 tracks. So once we solve it, we get the posterior distribution for each of the track. So we present the full results. We don't have p-value, but we do have some statistical evidence. That evidence is with the current data and the current model and the priors, et cetera, et cetera. This is the probability of each track, the probability of the group differences greater than 0, for example. The vertical green line is the 0 location. So you can judge, you can make your own assessment about the strength of each track's statistical evidence. You don't have to hide. You don't have to arbitrarily draw a line in the sand, right? So that's, I call it highlight but low height strategy. So this is the first data set. Well, you say you have this modeling approach. How is that compared to the traditional approach? So we can do model cross-validation and comparison. So one approach is to use different information criteria, right? So there are many of them, but here I adopted one. It's called expected log point-wise predictive density. So use that information criteria. The Bayesian multi-level approach is way much better than the univariate, in this case, the two sample t-test. You do 11 of them, right? Another approach to compare the models, the two different approaches, is called a posterior predictive check. So you basically, you have the original data, which in this case is the black curve in both plots. Well, the original data is not a curve, it's a dots. But here, for visual comparison, I plot out the kernel smooths the curve. So in that sense, the black curve in both plots, the black curve is the original data. So now I have the Bayesian model, then you can randomly draw from the posterior distribution. That's why you say that the colored clouds. So here for each plot, there are about 200 tiny curves. Each curve is random draws from the posterior distribution. So on the left-hand side is traditional approach. Mass univariate, in this case, two sample t-tests for each of the 11 tracks. So that's, you see the reddish clouds. On the right-hand side, the blue one is the Bayesian approach. There are subtle differences, right? So of course, both models are not perfect. We accept that, but the Bayesian approach is a little bit closer to the origin data at both the tails and around the peak area, right? So that's from this perspective, the model is, Bayesian approach is superior to the traditional approach from those two angles. So that's one demo data. The second one is I'm going to use the matrix data. It can be correlation matrix, right? So people have been talk about the so-called functional connectivity. There are other matrices like mutual information entropy, right? So you name it, many different types. But I'm going to focus on one particular case is the correlation matrix from multiple subjects. So we have number of RIs, number of subjects. So we have this matrix, usually it's symmetric, right? So focus on the upper or lower diagonal, right? Off-diagonal elements. So during yesterday and even this morning, there are many talks about how to deal with the issue, right? When you have a matrix data from multiple subjects. So the traditional approach, there are several tools listed here. It's say the trees, but not the forest approach. Basically, the massive universe, right? Each matrix element, you build a model, t-test or general linear model. In the end, as I mentioned, you make an implicit assumption about the distribution, which is uniform. You pay the cost of a multiple comparison issue, right? So those are the downside. How can we do differently? There are many talks in this conference. People have proposed strategies, but here I'm trying still a univariate approach. But let's see how do we in this framework, how do we deal with it? So let's use this toy example. Suppose we have 5 RIs. 5 RIs, you're going to have 5 times 4 divided by 2. You have 10 off-diagonal elements, right? Unique elements. So if you flatten those 10 elements, now we're going to look at the variance covariance structure of those 10 elements. Some of them are correlated, some of them are not. That's why you say in the big matrix, you say zeros and a row. Of course, that make a strong assumption because those they're correlated the same way. Unlike the multi-univariate approach, Jeff Morris was talking about yesterday. He was using that approach, right? So that's a little bit more probably generic. In my case, I make a strong assumption about the variance covariance structure. So that's I want to address the issue. We do need to take care of the relatedness, even though this is make a little bit strong assumption. So how do I build the model? With that matrix from multiple subjects, we can build one model. Okay, in this case, still have 3 indices: ij for the regions, k for the subject. So we still assume it's Gaussian or student t distribution. Then the mean, we decompose the mean into multiple components. We have the overall mean, average at the global level shared by all the matrix elements. That's B sub 0. Then the next 2, the blue ones, those are the contribution from those 2 regions because each matrix element involve 2 RIs. So that's why you say 2 contributions from each of those 2 RIs. The next one, the red one, is the interaction between each region pair. The next one, because each subject also have contribution at each RI, So that's why you say those are subject level 2 components. Lastly, each subject has their unique contribution. So then we make some assumptions. Those are the priors, right? Gaussian or student T, whatever, right? So we have some priors. So then we solve that. But in the end, we need to assemble the results, right? In this case, we only come back for each region pair, each matrix element. So that's why we assemble them. So that's how do we make inferences about either matrix element level. But the unique thing about this modern approach, in addition to each matrix element, we can also say something about each region because we decompose the effect at those at the region level. So we can say something about each region contribution. So that's something unique. That's a little bit similar to the so-called graph theory, called hardness, right? So that's the importance of each region. But that's the number of so-called connections in number of degrees, the discrete number. But here we have a specific quantity to characterize the relative importance of each region. So that's in this modern approach. We have a program implemented, and also the published paper describing the details. So let's look at a specific data set. So in this case, we have some number of subjects. In this case, we have 16 RIs. So with 16 RIs, we have 16 by 16 matrix. That means we have 120 matrix elements. So among those 41 subjects. So if we adopt that Bayesian modern approach, first of all, we can say something at the region level. So on the right-hand side, you say the posterior distribution among those 16 regions. So again, we don't need to hide the weak results. Everything is, everybody can make their own assessment about the strength of the evidence. And this shows basically at the region level. That's like I was talking about the hubless in graph theory approach. So this at the region level. If we go back to the matrix elements, so now we compare the two approaches. On the left-hand side, the traditional approach, massive univariate, right? In this case, it's a one sample t-test. So the color, there are two pieces of information. The size of the cycle, the circle, the bigger means the effect is bigger. The color, the darker, the strength also is stronger, right? On the right-hand side is the Bayesian approach. So side by side, you can see the traditional approach is much stronger, right? So if you have to draw a line in the sand with, one tail, two tailed, magic number 0.5, on the left-hand side, you can count there are 63 region pairs. On the right-hand side, the Bayesian approach, you still have to draw a line, there are 33 region pairs. You may say the traditional approach is stronger, right? But don't forget, you have to pay the cost of a multiple comparison. If you do that, none of them would survive on the left-hand side, right? On the right-hand side, you still say something, right? Regardless of where you want to draw the line. But anyway, so still want to emphasize, we present the whole results without hiding. Everybody make their own judgment. So in summary, I briefly talk about the limitations about the traditional approach. Then we propose a Bayesian multi-level modern approach, use the two data sets to demonstrate, and there's programs associated with those two modeling data types. All right, that's all I have. Thanks. I want to say thank you for my collaborators, and thank you for all of you attending my presentation. Thank you.
Now we will have our third speaker, Dr. Shuo Chen. He is an associate professor from the University of Maryland. His research focuses on modeling large biomedical data with complex and organized structures. His topic is L0 shrinkage in graph space for brain network inference. Sure.
Thank you, Qiong. So today I will also talk about some recent progress on brain connectivity and network inference. I think you have been heard a lot of brain connectivity background knowledge from this conference, and our study focused on brain connectivity networks across subjects. And for example, each subject can have a connectivity matrix for multiple brain regions. And the metric could be the correlation and other mutual information, other metrics. And the scientific question is to investigate whether the connectivity pattern across different subjects can be associated with some clinical symptoms, age, and other covariates. So So if we consider the data as a group of networks, so we have an adjacency matrix, either weighted or unweighted binary adjacency matrix from S subjects, and each subject can be considered as share a common graph space, like with the same number of nodes, which are the Bruin regions, and the connections as the edges indicate the connection strength between the Bruin regions. So essentially, we have the n nodes, and with v is cardinality, and the edges as n times n minus 1 divided by 2. And you can use a generalized linear model. So this is a pretty general format to see that the expected value of the connectivity matrix from subject S as follow a regression coefficient in n times n matrix, and as a covariance of the subject S. And then we can store the inference results by a W matrix and by N matrix for one covariance of interest. So here is kind of the demonstration for this situation. You have multiple connectivity matrices from multiple subjects, and for example, the two sample test difference, and you can see that we have a two group of subjects, and then we can summarize a matrix of the inference results of the W matrix. So it's also the n by n matrix. And if, for example, each node here can represent the negative log p value of the inference, and then the overall inference matrix will look like a heat map like this. The hotter points means more difference between the two groups, or more associated with covariance of interest. And the general scientific question is to see whether there is a subset of edges that with the kind of a regression coefficients not equal to 0. And it seems to be a multiple testing issue, but we want to go beyond the multiple testing issue and to see whether the differentially expressed edges will follow any organized topological structure, or we can call them subgraphs, and then whether we can perform the subgraphs and to draw inference whether the data-driven subgraph is associated with the covariance. And then the advantage of this method is we keep the spatial specificity of which edges with which nodes are differentially expressed between the two clinical groups or associated with the covariance, and which is kind of different from the commonly used network inference. This is because usually if you, for example, you want to test whether default mode network, whether it's different between the two groups, you would like to pre-specify the default mode network, and then you can use a summary statistic or loadings to compare each edges or the loadings between the two groups for the default mode networks. However, our method is kind of to use data-driven methods to show the covariance associated network by data-driven method. So in general, the connections in our data, all the data sets we have been analyzed seem to be altered systematically in the brain rather than individually or isolatedly, and we only find a small proportion often is of the edges are altered by the covariance. So you can see that on the left is inference results matrix. For example, we can consider each point as a negative log p value, and the two graphs are isomorphic to each other, which means if you just shuffling the order of each node to certain specific order, and then you can summarize the connections between the brain areas associated with the covariance of interest. And then you can specify the first one as a clique subnetwork shows the difference between associated with the covariance, and then this is a bipartite graph. associated with covariance. And the question is, how do you shuffle your nodes and identify the subgraphs can best identify the covariance-related subnetworks? And how do we achieve the high sensitivity and low false positive errors and in this kind of inference? So we just want to present this type of analysis using interesting Boltzmann entropy from Boltzmann entropy perspective. So this is kind of the Ludwig Boltzmann's tombstone, and he has the famous entropy formula on his tombstone. And then, so this is the formula as its entropy level equals the Boltzmann constant times log W. Oh, sorry, the W is mean difference than our inference matrix W. But in this entropy formula, the W is can be written by the n factorial divided by n1 by n2 if you're using the commonly used example of the Boltzmann entropy. So this is a kind of interesting. Just you assume there are gas particles in two chambers of a closed space. This is chamber 1, this is chamber 2. And at the initial stage, all the particles are in the first chamber, and then you open the valve, and then gradually the particles can go into the other chamber. And then you can use the formula to calculate the entropy level. Actually, you can imagine that the entropy level at the first stage is the lowest state with the value 0. And then the second state, you can see 6 particles pass through and 27 left here, and it is 6.7. And then you have more particles are more evenly distributed in the two chambers, and then the Boltzmann entropy increase gradually. And and here is just it's a kind of, you have fixed two chambers, and the entropy level is lowest when the gas particles are more concentrated in one chamber. And you can numerically calculate that by using the formula derived from the general formula from the Boltzmann entropy. And in many times, more general situation is you don't know the the chambers, and you can see the gas particles. You can even consider this as a Poisson point process and a point-Poisson process, and all the particles can randomly distributed in any space. And then a low entropy stage is when the more particles or dots are concentrated in small space, and when and gradually it can be less concentrated, and then you can go to a state called a Thermodynamic Equilibrium, which is similar to the homogeneous Poisson point process. And the entropy level, certainly this is the highest entropy level and the lowest entropy level. And certainly the probability of this state is the smallest, and the probability of this state is highest. And why do we mention this Boltzmann entropy is because we consider the differentially expressed or covariant associated edges in the graph space can be also following a low Boltzmann entropy state. That means if you consider a hot edge, for example, a high value in negative log p value as a particle, and then you in a burn connectivity study, the edges associated with a covariance will follow a distribution that is latent, but it's latent in this graph. But after you do certain algorithm, you will find them can be concentrated in certain subgraphs. So in other words, you can use a set of small-sized graphs to cover most of the informative edges. Please note there's a difference that in the gas state, particles can go anywhere without any constraints. But here, each edge is constrained by 2 nodes. And if you define a subgraph like this, you can only cover those edges. The other edges connected with these nodes cannot be included. And you can also define your structure of the subgraph. For example, here is a clique, and here is a bipartite graph. And you can also define some other subgraph based on your discovery. And so based on our analysis, we find when we summarize a subgraph with high concentration and a larger network in size and the high concentration of informative edges, all the statistical performance in terms of power and false discovery rate are much better than the regular large and less dense subnetwork inference. So essentially, we can extend the Boltzmann entropy into kind of a certain entropy is more related based on the discovered subgraphs, which is related to the number of informative edges in a network. So suppose we have a capital C number of subnetworks, and then within each network, we have this number of informative edges, and this area is the number of total edges in this subnetwork. Then we can show that the entropy is a proportion to the negative of this value. So essentially, if we do subnetwork work discovery in the right way, the low entropy state will reveal more organized patterns in the subgraph. So so there are many ways you can summarize the subgraph that are associated with the covariance. And we consider that the subgraphs with the lowest entropy state will be the ideal or the goal we want to achieve, because later we'll show it can achieve the highest power and lowest false discovery rate. And also we want to, later we'll also show under the none of no network exists that the entropy level is high, and there is no isomorphic graph can be discovered showing the subgraph associated with covariance. And I want to point out is all these 3 graphs are isomorphic. So essentially, if you do some embedding, if you project all them into an embedded space, they are just identical to each other, which is differential from the none situation, which is no edges is associated with outcome in an organized pattern. So we have done many analyses on different covariance and networks, and we found most of our results that is a kind of a certain clinical condition is associated with organized pattern of brain circuitry. So this is also that it's well organized, and although they have different topological structure, the entropy level is similarly very low for each condition after revealing the true subgraphs that's associated with the covariance. And so for the model, we first consider the testing hypothesis is just to see whether for example, the inference of individual edges in the graph is a random graph, or they follow an organized distribution to say that at least one covariance-related subnetwork exists. So this is relative to a high entropy state. This is relative to a low entropy state. And under the none, the graph is a random graph, and you can consider each edge has equal probability to be a non-none edge that associated with covariance. And then there's no subgraph exist that associated with the covariance. That means no matter how well you can do the subgraph detection, there's no subgraph that is concentrated with edges with small p-values. That is the null. And and if the alternative is true, then we have the latent low entropy state with organized subgraph. And then some edges in certain subgraphs can be associated with the covariates, and the concentration of the edges in those subgraphs will be very high. And then our goal is to make inference on each subgraph in data-driven detected by using the lowest minimal entropy principle that and then we can test them each subgraph we detected with multiple test correction. And we first talk about the graph under the none, and essentially there's even though there could be individual edges associated with covariate, those edges, just like the red edges, are not distributed in organized pattern. That means if you embed this graph into embedded space, it essentially have the homogeneous Poisson process, like the first speaker mentioned, that it will just because there's no organized pattern, and and no matter how you shuffle the order of nodes, the level of entropy is equivalent high, and you can consider its expected value as invariant to the shift of the order of the nodes, because no subgraph can be detected. And under the none situation, we just summarize a lemma that to show that we want to show that it's very unlikely if you can, under the none, you can observe a relatively large subgraph that can concentrate with edge with small p-values. So we can show that the probability of such graph with a high density and a relatively large edge the probability can quickly converge to zero with the increase of the size and the density of the subgraph. So that's actually is well aligned well. It's aligned very well with our entropy formula developed in the introduction section. So we kind of develop just to recall that the low entropy formula is you have the high number of informative edges in the small subgraphs. So essentially is we want to increase the weights of the edges in all the subgraphs while to control the size is of the subgraphs. And we have developed several algorithms to implement the function, and we relax the structure of the subgraphs from the clique, the community to the tripartite graph to interconnected subgraphs. And if you're interested, you can see these methods from our website, or you can send me email for the for references. And and we interestingly notice that if you have the C to be the number of subnetworks or subgraphs, so total number of subnetworks, including the singletons in the overall graph, then the overall L0 penalty term is bounded by this C. So essentially, is the C number is higher, and then the L0 penalty term is kind of is smaller. So essentially, is we can show that the edges constrained by the nodes can be influenced by the number of subgraphs or subnetworks we select. So we implement this type of subgraphs to identify all type of we extract the subgraphs from the overall image, like overall W matrix like here. And this objective function implementation is different from the traditional subnetwork or community detection. For example, this is the original input of the W matrix, and you can get the spectral clustering results like here. And you can use the Leuven's methods like the C and the D. And the D is the infomap random walk. And you can see this is our method. So in that, we can show that the algorithm based on our objective function can provide optimal and consistent estimate of the underlying subgraphs, and which is different from the traditional community detection because we did the Arroyo zero shrinkage to achieve the low entropy state. We want to use a small subgraph to cover more informative edges. This is a low entropy state. In traditional community detection algorithms, they want to just allocate nodes into communities to ensure that edges in that are highly with the higher weights. And so we have some properties of the algorithm, and then we can do permutation test on we can do the permutation test on the to make inference on each extracted subgraph. And so the permutation procedure can mimic the non-distribution of the high entropy state, because under the no edges is associated with the covariance. And then we build a test statistic based on the lemma 1, which can incorporate the size and the density of the subgraph. And then we this procedure can make an FWER inference on each subnetwork. And certainly, of course, we have the theory to support that the larger and the denser subgraph with low entropy has more power and and actually lower false positive error rate, and because it's rare to find. And then we show that with a data example with one primary data and one validation data sets, that the first include 70 versus 70, and then we have the replication data with the 13 versus 30 of schizophrenia patients and the normal controls. And we can quickly get into the results. Here is the original. I think we use this is kind of the central sphere of the AL postulation. And here we just show the W matrix of the primary data set. And then we find one network significant associated with the disease status. And then we separately run the algorithm and then detect another subgraph from the validation data set. And we find that the finding from the first data set is highly overlapped with the second data set. So I think it's just that the first one has 20 nodes, and the second one has 21 and 22, and there's only one node different between the two data sets. And similarly, we run MBS. MBS revealing no significant results for both of data sets is because of the network, differential express network from MBS doesn't do the Arroyo zero shrinkage and doesn't allow the low entropy state of the subgraph. So it's when the number of nodes increasing, the power can decrease very quickly. And if you do individual, just like Don mentioned, the multivariate inference FDR show no difference. Even you just rank all your edges by p-values, and then the first data set show 430 edges, and the second show 22, and there are only two is overlapping between the two. And the altered the network is a kind of is a combination of the default mode network, a part of that, and the salience network and the executive network, which are all associated with schizophrenia. And then we And this is also new. We find that all three networks, the interconnection between the three networks, rather than each network alone, is associated with disease, which is also new, and because it's data driven. And then we also do some inference to see whether we can detect the network accurately, and whether the edges in the network can be accurately recovered. So so the performance of my method is very reliable. So in summary, so we kind of trying to find some classic Boltzmann entropy model to link with our network inference. And we found that actually all the entropy level of many applications in the biomedical research, including the co-expression of DNA methylation or RNA expression or linkage discriminant in genome, they all show very low entropy Boltzmann or graph entropy state. And this state method can be also applied to dynamic networks to make sure the change from one network state to network state is follow a low entropy state. And essentially, that's pretty much of our talk. And so lastly, I would like to thank my co-authors, Qiong and Yuan from Ohio State, Peter and Elliot from our center, and the NIH grant. And since it's a talk at Emory and the CBIS, I would have special thanks to the founders of CBIS at Emory, as Du Bois and Ying. I think Du Bois is not here, but I posted his picture here. Yeah, that's it.